Okay, so last class we finished up with mixer noise. So today we'll continue with TX architectures. So probably we won't do much on TX architectures because really there are only one or two ways of upconverting a transmitted signal, at least the signal you want to transmit. So we'll cover that in today's class. Maybe we'll start off with the receive architecture. We already know something about the receive architecture. Whether we can do something better than what we already know, right? That's what we want to find out. So over the next couple of classes, we will cover RX architectures also before we go on to the other components. The basic idea why we are doing this is so that the course is structured such that you can also do some projects along the way. Obviously, the best way to target this would be to do maybe all the system level stuff first, then start doing the circuit level, block level topology. But then the course cannot be structured very well in terms of projects. So that's why what we did at the beginning, we got some idea as to how our signal is transmitted and received. We looked at the heterodyne and homodyne receivers. Then we immediately jumped into what we are going to do at the block level so that you can get along with your projects. And then we come back to the architecture. So as we mentioned in last class, so we have three ways of representing a signal. So the first one, we have x of t is a of t cos of omega naught t plus phi of t. So a of t is the amplitude modulation and phi of t is the phase modulation. Then you have the Cartesian representation. So the Cartesian representation, you have the signal x of t is decomposed into an in-phase component and a quarter-shell component. Okay? Remember, these two could be independently modulated, or what you could do is you could take your polar form and then convert that into the xi of t and xq of t form, where each one of these will depend on a of t and phi of t. And the third one, which we will not concentrate much, is the complex envelope. Where x of t is written as the real part of some x tilde of t e power j omega lot. Okay, so this is very useful for certain band pass representations, but primarily the ones which are very commonly used are these. Okay, and if you see, most of your transmitters and receivers are targeted towards these kinds of representation. Depending on what kind of modulation scheme you are using, either one of these could be more useful for either the transmitter or the receiver, right? In general, what you will find is most receivers would use the Cartesian representation, where you try to split the signal into its in-phase and quarter-shell components. The transmitter, on the other hand, can have either the polar or the Cartesian representation, because coming from the baseband into your upconverter, you can actually either have the baseband produce the in-phase and quarter-shell components, or have it produce the amplitude and phase components. Now, each of these ways has a certain advantage or disadvantage, and depending on the specific case, you will choose to do one or both of these. What was the example we took for the polar representation? Let's say we are specifically talking about a polar transmitter. For example, a polar transmitter would probably be more efficient for purely phase modulated signals. Right? And there are many examples of these. For example, the original GSM signal was purely phase modulated. There was no information sent on the amplitude of the signal. It was purely in the phase of the signal. Similarly, the original Bluetooth signal was purely phase or frequency modulated. It doesn't matter for these purposes whether it's phase or frequency modulated. But if the signal information is either in the phase or the frequency, you will choose a different kind. You could choose a different kind of architecture. Now, even in the case where a phase modulated transmitted signal exists, you can choose to do a Cartesian representation. So what would be the relative merits of doing a polar transmitter versus a Cartesian transmitter? Well, first of all, what do we mean by a polar transmitter? So let us say if I had a polar transmitter, so I had only a signal phi of t coming in, right? What do I need to do to send this, to transmit this signal? I need to upconvert it, correct? I probably need to amplify it so that the received signal strength is very large. Anything else? I need to upconvert it and maybe amplify it before I send it into an antenna. Anything else? Amplitude modulation. No, assume that I have only phase modulation. I have a purely phase modulated signal. I need to upconvert it and send it through a power amplifier, right? How would I upconvert it if I have a phase modulated signal? So I have a signal phi of t which represents the phase of the signal I am trying to transmit. How would you upconvert it? You need a circuit or a system which actually processes purely the phase of the signal, preferably. What kind of circuit do you know that does that? A PLL. A phase lock loop, processes the phase and or the frequency of the input signal, right? So if I were to, let us take all of you know what a phase lock loop is? How many of you do not know what a phase lock loop is? Okay, good. I'll draw the simple representation of a phase lock loop. So FREF is your input signal, which is a constant, a very, very pure frequency reference. And you take your output of the VCO, divide it down by a particular factor to get your FDiv, and you compare FREF and FDiv, and the PLL drives FDiv to be equal to FREF, and hopefully also it will also be able to drive phi div to phi ref. Okay, so it drives the output phase and frequency to be equal to the input phase and frequency. Is that okay? Now, if you had to write this in terms of the output frequency in terms of the input frequency, the output frequency is the divide ratio times the input frequency, input reference frequency. I think so this most of you should have learned by now in some course or the other. Now, what is the transfer functions of the PLL from the input to the output in the phase domain? Amplification by n. Okay, anything else? Sorry? Okay, good. So you have two characteristics from input to output. Your phi out is some n times phi ref. Okay, and what else do you know? It is a low pass transfer function. The bandwidth of the low pass transfer function really depends on the PLL parameters, right? It depends on the charge pump current, the loop filter value, the end divider, the VCO output frequency, everything, all of these factors. So now what do I need to do? If I want to transmit a certain phi of t at the output, what do I need to do? At the VCO you can give phi of t. Here? Okay. So he says at the VCO, at the input of the VCO, I can give a phi of t. Will that work? What is the transfer function from the input of the VCO to the output of the VCO in the closed loop form? It is a high pass transfer function. Okay. Again, the cutoff frequency of the high pass function will depend on the loop parameters, right? So if you actually give a phi of t at the input to the VCO, it will be high pass filtered. So if let us say the bandwidth of phi of t was 1 megahertz. Okay. So let us say phi of t had a bandwidth of 1 megahertz. Let us say the loop had a cutoff frequency of 100 kilohertz. What would happen? All the signal content below 100 kilohertz will be filtered out, right? So you need to do two things. Either you need to move the PLL bandwidth really low, such that whatever you cut off from phi of t does not matter, but you really don't want to have a very specific case like that, where you want to push the PLL bandwidth really low, because the minute you do that, your PLL lock time, right, settling time, all of these things will become really slow. Okay, so you don't want to do that. How else would you do it? Or let us take the simpler case. So let us say this was 100 kilohertz signal. Let us say this was a 100 kilohertz signal. That's the simpler case. How would you do it? How would you transmit it? Okay, so one thing you can do is send phi of t here. Maybe not just purely phi of t, you will have to take into account whatever transfer function happens from this input to the output, right? And then maybe later on, maybe in the after f0, after this point, maybe you have some divide by 2 or divide by 4 or something else. You have to take into account all of these when you actually decide what signal to put in, but you can actually modify phi of t and give it to the input of the PLL. So instead of having a pure phi ref and f ref, you would actually have a phase modulated signal going into the PLL, okay, whose frequency may be constant, but the phase is varying over time. That same phase will get transferred to the output of the VCO at the VCO frequency. So you are actually doing upconversion using the PLL. Is that clear? So that is one way to do it. The second way to do it is to actually give phi of t to the divider, because you know that the output phase and output frequency is a function of the division ratio also. Okay, so there are many cases where you have a fractional divider where you are actually able to change the output phase or frequency with a very fine step. Maybe the signal has only maybe 12 bits or 13 bits of worth of data, but you can actually go to maybe 18 bits or 20 bits easily to select the frequency or phase of the VCO, of the PLL. Okay, so in that case, it may be a lot easier to actually just supply the data through the division ratio. Maybe to get the output frequency to a particular accuracy, you maybe had 18 bits of division ratio, integer plus, let us say 18 bits, right? I had a fractional division ratio to actually allow me to select intermediate frequencies also. Now, all I have to do, if I want to vary the output phase, all I have to do is change a certain number of bits here at a certain rate, and that will actually change the division ratio. It will change the output frequency, and I'll get a certain spectrum. maybe at the output, I may get a spectrum like this if I vary it in a certain way. I can choose what kind of data and at what rate I'll put it into the end divider such that I actually get a certain output spectrum. Okay. So this is one way of doing it. Obviously this is somewhat of an advanced way of doing the phase modulation because there are lots of details you have to take care of. Apart from what is the transfer function of the phase, you will have to worry about what the bandwidth of your input signal is. Obviously if your input signal has a bandwidth larger than 100 kilohertz but the loop bandwidth has only 100 kilohertz, you cannot do it either here or here. And you can't do it here also. One of them is a low pass, the other is a high pass. How would you do it? Let's go back to our 1 megahertz case. How would you actually use this to transmit a 1 megahertz phase modulated signal? Exactly. So what you do is split the input phase modulated signal into two portions. One goes from 0 to 100 kilohertz. The other goes from 100 kilohertz to 1 megahertz. Right? So the low pass signal will actually be sent through this path or this path, and the high pass portion of the signal will be sent through this portion. Is that clear? Obviously you will have to match the gains through the different paths. You have to be very careful with that. Okay, so which is why I said this is somewhat of an advanced way of doing the modulation. However, you have many nice things going for you. Obviously you already have to go through and go ahead and build the PLL for any transceiver. For any transmitter you already need a PLL. What is the extra circuitry you need to actually do this modulation? Not much. Okay, because you anyway had your fractional divider and you had static data going in. Now you have maybe a very low frequency 1 megahertz data going in. Getting your fractional path to work at 1 megahertz is very straightforward. No problem with that. Same thing goes with this path also. Same thing for the reference path also. 1 megahertz is very small, very low frequency compared with what the signal frequencies we are talking about. And same thing with this side also. Okay. So really the extra circuitry you are talking about is not very complex. However, what really leads to the complexity of this kind of transmitter? Two things, right? Number one, matching the transfer functions from input to output, from the reference to the output and input of the VCO to the output can be extremely difficult. Number two, the bandwidth of the PLL will change over process, voltage, temperature. Right? So you will have to find a robust way of actually splitting the signal and matching the transfer functions. Really, most of the work goes into doing that. The third thing is, even though we talked about 1 megahertz signals, most modern signals are not restricted to 1 megahertz. If you look at the original GSM signal, it had 100 kilohertz. Okay? And the original Bluetooth signal, which we gave as an example, also had something like this. So they were all very, very narrow band signals, purely phase modulated narrow band signals. This kind of transmitter worked really well. Okay? As we moved on, we actually wanted to transmit more and more data, and the more data you want to transmit, the bandwidth of the signal keeps increasing. And today we are talking about 4G systems or wireless LAN systems, where at a minimum you are transmitting data at 20 megahertz. Right? The bandwidth of the signal is 20 megahertz. We are talking about wider bandwidths also, but let us take the example of a 20 megahertz signal. Okay? Obviously, people have realized that sending data only in the phase of the signal is not good enough. You are really wasting the amplitude of the signal. Spectrum is actually very, very precious. You can't just waste spectrum by transmitting only in the phase. If you transmit in the amplitude, you burn a little bit more power, but overall the efficiency of the system becomes much, much better. Okay? So, most of today's signals have information in both the amplitude and the phase, including the newer versions of Bluetooth. So if you look at Bluetooth version 3 and version 4 and so on, all of them have something like 3 megahertz signal bandwidth, and there is information in both the amplitude and phase of the signal. Same thing with the cellular signal. We started off with GSM, but after that we have something called Edge, which is supposedly the next version of GSM, where apart from phase modulation, we also tacked on amplitude modulation. And now, of course, the LTE signal, WCDMA and LTE signals actually have information in both the amplitude and the phase. It is not a purely phase modulated signal. Okay, it is more of a quadrature amplitude modulation, QAM kind of scheme is used in these kinds of signals. So if you actually try to take these signals, very wideband signals, and with very dense modulation, and look at the information contained in the phase of the signal, what do you think you'll find? So let us say I take a 20 megahertz wide LTE signal. Okay, I try to look at the phase of the signal. So I have an LTE signal which is originally Xi of t plus Xq of t. I am going to rewrite this as A of t cos psi of t, let us say. Okay, I am going to split it as amplitude and phase. What do you think the bandwidths of the amplitude and phase modulated signals will look like in the polar domain compared to the bandwidths of the Xi and Xq? Now this will really be a function of what kind of modulation you use, as well as the details of that modulation. But what you will find is that if Xi and Xq have bandwidths of 20 megahertz, for many of these modern signals, if you look at the phase of the signal, the actual bandwidth of the phase modulated signal is much wider. Okay, maybe 4 to 5 times wide. It really, the exact factor really depends on what kind of modulation you are using, but it is much wider. So now, starting off from a 200 kilohertz signal or a 100 kilohertz signal, you are talking about transmitting a phase modulated signal of maybe 100 megahertz. This is really wide. Okay, and you are talking about using circuits to process these. They will be power hungry. Getting the transfer functions to match over this kind of bandwidth is extremely difficult. Okay, so therefore you will find that these kinds of transmitters are not very good for modern signals, modern dense signals, right, where the information in the in-phase and quadrature components are very wideband as well as very dense. Now there are a couple of other ways of doing this. I'll also show you that. I could have PLL1 which had FF1 which produced your F0. Okay. I could have a second PLL, okay, which produces the phase modulated signal. And I could actually mix these together to actually give you your phase modulated signal. There are really many different ways of doing this phase modulation using PLLs. Now in this what you are doing is, instead of using the same PLL, you are actually using a different, maybe a low frequency PLL to make the phase modulated portion easier, and then you are mixing it with the high frequency PLL to actually add the two. Now obviously you need to look at the non-idealities of the mixer itself. Mixer will produce spurs and so on, phase noise, spurs, everything. But people have done these kinds of topologies before, these kind of architectures before for these kinds of transmitters. Yes. Mm-hmm. Yes. Exactly. Yes, absolutely, that is right. So if you look at the modern kinds of signals I am talking about, many of them actually use what is called quadrature amplitude modulation. So they actually use finite transitions in xi and xq. Okay. They use finite transitions in I and Q domains. Technically it should just be I and Q. Xi and xq are the signals. Okay. So this is an example of what is called quadrature amplitude modulation. Okay. Many of them are actually built for something like this. Therefore, when you actually look at the phase domain, they have a much wider bandwidth, or rather you really can't predict what the bandwidth of the signal could be for a particular error in the signal. Obviously, if you start clipping the bandwidth, you can still get back the signal, but you'll get a certain bit error rate or a certain error vector magnitude. For a minimum cutoff on the error vector magnitude, maybe 1 or 2%, you are looking at something like 4 to 5x limitation in bandwidth. Obviously, you could also design your signal such that it has information in the phase modulation and the amplitude modulation. You can choose the transitions as well as the modulation scheme such that it's more optimized for phase modulation. The only difference is, if you do it that way, there is a possibility that if you, let us say, make sure that the phase modulated signal still has a bandwidth of maybe only 20 megahertz, it's easy to process it, you might find that the AM portion of the transmitter may get really complex, because the peak to average ratio of the AM itself could be much higher than what you want. You have to optimize both paths. It may be easier to optimize two I and Q paths separately compared to an AFT and phi-ft paths. Okay, so that is so far for polar modulators. If you really have to build an IQ modulator, what would you do? You have to take a signal which is represented in the Cartesian plane and transmit it. You need to upconvert it, maybe amplify it and transmit it. What would you do? So of course, let us take the simplest example, the Cartesian example of a direct conversion transmitter. So this is the first case of the polar TX. The second case is the Cartesian direct conversion transmitter. I have xi of t and xq of t. So I am going to mix xi with cos omega LOT and xq with sin omega LOT. I'm going to add the two. What I have here is x of t equals xi of t cos omega LOT. This is the representation we saw for the complex signal x of t. Maybe I didn't put it down explicitly here. So this was a more of a, let me write that down properly. Okay? Because that was the xi plus jxq is the baseband signal. At the RF it will be xi of t cos omega lot minus xq of t sin omega lot. Then after that I have a power amplifier probably, and maybe a matching network. What else do I need after the matching network? Now depending on what kind of transmitter I have or what kind of transceiver I have, the output of this power amplifier, which is driving a matching network, could go to two kinds of systems. If you have a time division duplexing system, okay, you need a transmit receive switch. Okay, to actually multiplex between the TX and the RX. So the TR switch basically connects, during transmission it connects the antenna to the transmitter, during reception it actually connects the antenna to the receiver. So this is one possibility.
How does this realize?
It's very easy, right? Using a switch. Yeah, of course it may not be a MOSFET switch. If you want a really high quality low loss switch, it could be maybe a HEMT switch or an HVT switch. Okay. What about if you have a frequency division duplex system? So in other words, I am transmitting and receiving at the same time, but the TX and RX frequencies are different. What happens then? So this block is called a duplexer. Okay. What this does is it allows the transmitted signal of one particular frequency to go from the TX port to the antenna port. At the same time, it allows the RX signal to actually go from the antenna port to the RF port. Okay, so it has a frequency dependent behavior. And the third thing you obviously need is you need to make sure there is very little transmission from your TX port to your RX port. Okay, you need very good isolation from your TX to RX. Is that clear? And we are soon going to see why we need that. So this is your baseband signal. Okay, so you send it through a mixer, up converter. Obviously, I have not shown all the details. You might want some upfront analog filtering. You can put that in. You might need some RF filtering. You can put that in. But this shows the bare bones direct conversion transmitter. All you have to do is multiply it with cosine and sine, add the two outputs, send it through a power amplifier. Obviously, this power amplifier needs to be a linear power amplifier. Unlike the polar case where you did not have any amplitude modulation, you could send it through a saturated power amplifier. Actually, it really depends on the exact system you're talking about. Because if you try to realize the switch on chip, it will naturally have a lot of loss. Okay, because the loss versus isolation trade-off in a MOSFET switch is not very good. Okay. Now, earlier when we were talking about 15 years ago, the MOSFETs are much lower. So, to actually realize a low loss, you had to have a very, very large MOSFET. So, the isolation would necessarily be bad. Nowadays, I expect you can make a much better TR switch. So, it should be possible in many systems to integrate the TR switch inside your system. But what you will find is TDD systems are now falling out of favor for many of these applications. Okay, because duplexers are also very widely available. So and they are also seen as more efficient. and there are many issues with TDD systems which you don't see in FTD systems. The most important one being you're actually turning on and turning off the transmitter at a certain rate, right? So when you actually try to turn on and turn off a very high power amplifier, what happens is this causes a lot of interference with many other circuitry on the same chip, okay, or on the same system, because the power amplifier is very outputs a lot of power. We are talking about anywhere from hundreds of milliwatts to several watts, and what happens is this power actually couples magnetically or maybe through the substrate, maybe through the power supply to other circuits, and that causes interference. Whereas in an FDD system, you are transmitting and receiving all the time. You are not doing this periodic on and off. Okay, so because of that, you will find that FDD systems are much more common. But I am pretty sure there are many cases where you can realize the CR switch on chip. Okay. Okay, so what are the critical parameters we are interested in? Let us take the example of the direct conversion transmitter. What are really the critical parameters we are interested in? We said that for a transmitter, we are primarily interested in linearity, efficiency. These are the important parameters. Anything else? How about noise? How about in-band noise? In-band noise is not considered a very important parameter because you are really generating the baseband signal, and you could generate it at a large enough amplitude such that the noise is not very critical. And we already talked about this. In a receiver, you are receiving signals of the order of maybe minus 100 or 110 dBm. So that works out to, at 50 ohms, that works out to maybe less than a microwatt. In the case of a transmitter, you can easily generate signals which are several tens or hundreds of millivolts. So that is not a problem for us. Now there is one more parameter which is important. There is one more parameter which is the noise in the receive band. What do I mean by noise in the receive band? We talked about the finite isolation from the TX to the RX. Even if the RX frequency is offset from the TX frequency, so let us say I was not transmitting any information, I was just trying to transmit a single tone. As we will soon learn, you never get a pure tone by itself, you always get some phase noise which goes together with your tone. Okay, because the phase or the phase of the signal which you are trying to produce, it will never ever be pure. You can try to make it as low noise as possible, but it will always be corrupted. And if you look at the phase noise curves of the signal you are trying to produce, it looks something like this. And if this is, let's say, 30 dBm, and let us say the phase noise is, let us take let's say 130 dBc at a particular offset, minus 130 dBc per hertz at the RX offset. Okay, this means you are actually putting out around minus 100 dBm of noise, of phase noise into the RX band. Okay, this will not be acceptable. Now if you have this is on the transmitter side. If your duplexer has a certain rejection, okay, if your duplexer has a certain rejection, then you will be okay. Because if the duplexer has 100 dB rejection, for example, then you have basically cut this down. Okay? You have cut down this noise. Unfortunately, practical duplexers will have finite rejection ratios, maybe 40, 45, 50 dBc. So this may end up going to well below your receive signal. However, you want to make sure that the signal to noise ratio is also preserved. Now it's not enough if it is just slightly lower. It needs to be much lower than the signal to noise ratio at the end of the receive chain, right? Such that it doesn't degrade the signal to noise ratio. Or to put it in a different way, if the transmitter is outputting certain noise in the receive band, it will degrade the effective noise figure of the receiver by a certain amount. Okay? Can degrade the noise figure of the receiver by a certain amount. And you will need to take this into account when you are designing the receiver noise figure. You will have to think about, if you have an FDD system, you will have to think about how much of the TX power is actually leaking through into the RX band, how much of the TX noise is leaking into the RX band. So this will be a specification for the transmitter itself. I can specify for the transmitter saying the noise should be minus 130 dBc per hertz at this frequency, minus 160 dBc per hertz at this frequency, and so on. That will tell you how much noise is coupling through. Now, this is okay for an FDD system. If I have a TDD system, is this a problem? Not at all, right? My own receiver is not working when my transmitter is working. However, my receiver can be working, my transmitter can be on when somebody else's receiver is working very close to me. If I have a GSM phone, he has a GSM phone, and I am talking with somebody, he is talking with somebody totally different, right? What happens is, my transmitter should not degrade his receiver's noise figure, right? So there will still be a specification as to how much noise the transmitter can actually put out in the receive band. Okay? So okay, this can happen in both TDD and FDD systems. And as I mentioned before, PA pulling is important in so the PA power, high power, can actually magnetically couple and pull the frequency. For example, what I mean is, I have the PLL which is actually generating my frequency. Maybe this goes through a divide by 2, or let us take the simplest case. This actually goes directly into my mixer. Okay? I have my baseband. I have my power amplifier. Let us say the power amplifier had a turn on transient which looked like this. Right? The power on signal comes out, it has a certain rise time, fall time. So the PA is turning on maybe very fast. Okay? Because the times we are talking about are in terms of milliseconds or maybe even hundreds of microseconds. The PA turn on and turn off time periods. Okay? So when the PA is turning on, can you also turn on and turn off the PLL? You can't, because the PLL turn on and turn off times are actually could be much longer. Okay, because after you give the turn on signal for the PLL, it may take several hundreds of microseconds or maybe several milliseconds to turn on, because the time constants we are talking about are much larger. Okay, so normally when you do this TDD system turning on and turning off, you will not be turning on and turning off the PLL. You will only be turning on and turning off the open loop system, maybe the transmitter, the up converter, filters, and so on. Now when you turn on the power amplifier, what happens is the because of the PA turn on transient, it is suddenly pulling in a lot of power from the supply. Maybe you get a very big jerk on the supply. Similarly, the PA may use an inductor which may be magnetically coupled to the inductor in my VCO. Okay? So what happens is, normally when you try to do something like this, the VCO frequency will go off momentarily and then come back on. Okay? Because the PA is not turned on completely, it will pull the VCO away from its original operating frequency, and obviously once you have reached steady state, it will come back to the PLL will always set its output frequency correctly. The problem is the PLL takes a much longer time to settle. Okay? You do not want this in a system where you are turning on and turning off every so regularly. The classic sign of this will be, you have a turn on and turn off time, and what you'll find is, if you look at during this turn on period, let us say it look like this, you can actually plot the EVM as a function of time. Okay? And what you may find is that the EVM may look like this. This is your steady state EVM. Okay? However, because your frequency is way off, all your transmitted signal is completely different from what you wanted to, so you will get a spike. And if you get a profile which looks like this, it is most probably because of PA pulling. Okay? The EVM looks very bad at the beginning of your turn on, and then slowly it settles down to its original value. How do you solve this problem? Well, obvious solutions are, don't share the power supply between VCO and the PA, so that is PLL and the power amplifier, that is don't share PA supply. What else can you think of? Hopefully if the PA is on a different substrate, it will help, because you will not have substrate pulling. What else? Maybe place the PA very far away from the VCO so that you don't have magnetic coupling. Anything else? But you will always see some form of coupling or the other. Okay? You try to eliminate everything, there will be some circuit path through which, because see, the power levels you are talking about are widely different. Okay, the PA is outputting maybe 35 dBm of power. Okay, so even if the coupling ratio is very small, it will still disturb the VCO in some form or the other. So what is can anybody think of any other way to prevent the PA from coupling? Do not turn off the PA, obviously. If you do that, your efficiency will be really, really bad, because PA is the number one power hungry block in the overall transceiver. Okay, so you cannot afford to not turn off the PA. So, differential PA, okay, so that is a pretty good idea. But again, a differential PA in terms of efficiency is worse than a single-ended PA. Okay. Okay, so the best thing you can do is use a different frequency. What do I mean by different frequency? Can you ever transmit? Can the PA not transmit at your required frequency? It can't. So the PA operating frequency has to be equal to the transmitter frequency. However, the VCO itself need not operate at the transmitted frequency, because we know of many ways to generate different frequencies once you have a certain frequency reference. Okay, so you can use different frequencies for the PA and the PLL. For example, I can have a so which creates F1. I can have a two PLLs which generate two different frequencies, F1 and F2. Okay, and I can have I and Q. And this is LOI, LOQ of F1, correct? I do this. Maybe I do a band pass filtering here. F2. Maybe I can do something like this, right? I can do two levels of mixing, right? This is like a heterodyne transmitter where F1 and F2 are not directly related to FT, okay? Because the PLL and your PA are, the PLLs and the PA are operating at different frequencies, the chances of pulling are much lower. Yes? Actually, in steady state there is no problem. Now, all I'm saying is, if your PLL is at the same frequency of the power amplifier, the coupling mechanism will be much stronger than if you actually have the PA working at a different frequency. Okay, this is a very practical case. Now, I'll give you an example. Either the magnetic coupling or the substrate coupling is a function of frequency. Let us say the output frequency was 2 GHz. At 2 GHz, the coupling was very strong because the capacitive coupling paths are very low impedance, right? And the magnetic coupling may also be stronger. But maybe the two PLLs are working at only 1 GHz each. That is an example, okay, where the coupling mechanisms are weaker. The other way you could think of this, the PA has a certain power on transient. Now, how fast you turn on will also decide how strongly it pulls different frequencies. The rate at which you turn on the PA will also determine how strongly it pulls, and this will be a function of frequency. Okay, if you do a transmitter like this is a heterodyne transmitter. Okay, obviously there are certain things you need to worry about. This is kind of a little bit of a brute force approach to this problem, because now you have just added a band pass filter, two band pass filters. Okay, they need to be high Q, especially this guy, because the first one at least was an IQ mixer, so you only get a single sideband. For the second mixer, you actually get both omega 1 plus omega 2 and omega 1 minus omega 2. The omega 1 minus omega 2 term will need to be filtered out very strongly, because this is a transmitter. You cannot afford to be transmitting at frequencies other than what you are allowed to. Okay, so this band pass filter has to be really, really high Q. So this is a little bit of a brute force solution. There are some easier solutions which we'll look at next class. Okay, and then we'll continue on to receivers.